A piece of malware that works on only one operating system is inconvenient. A piece that quietly adapts across Windows, Mac OS, and Linux is a different class of problem entirely. It assumes diversity is not a defense, but an opportunity. Welcome to BlueHat Cybersec Academy. That assumption is increasingly valid. Modern environments are rarely homogeneous. Employees use Windows laptops, developers rely on Mac OS, servers run Linux, and cloud workloads blur all boundaries. Multi-platform malware is designed precisely for this reality. So in this session, we are going to break this down in a very practical way. How cross-platform malware actually works, why it is becoming more common, and what defenders often miss when they assume operating systems are separate security worlds. And most importantly, what signals actually matter in real environments, not theory, but observable behavior. Now, to understand why multi-platform malware is not just a technical upgrade, you have to look at how attackers think. At first glance, writing malware for multiple operating systems sounds like extra engineering effort. In reality, it is often the opposite. It is a strategic optimization. Attackers are not trying to support all systems equally. They are trying to maximize infection probability while minimizing redevelopment cost. That happens through a few recurring design choices. Shared codebases, often written in Go, Rust, or Python. Modular payload design. Platform-specific execution wrappers. And heavy reliance on cross-platform services like cloud storage, browsers, and SSH tooling. And the key insight here is important. The malware is not cross-platform because operating systems are similar, but because attacker tools increasingly avoid OS-specific dependencies. Now let's walk through how it actually works, because in practice, there are three dominant design patterns that keep showing up again and again. The first is cross-compiled binaries, what you can think of as write once, compile everywhere. Languages like Go and Rust allow attackers to take the same source code and compile it for Windows, Linux, and Mac OS with minimal changes. What makes this powerful is not sophistication, it is consistency. You get the same logic across platforms, the same command and control behavior, and even similar detection signatures, which sometimes becomes a weakness and sometimes a strength for defenders. The trade-off for attackers is larger binary size, but in most real-world stealth campaigns, that barely matters. The second pattern is interpreted payloads, which rely on environments that already exist on the system. So instead of compiling anything, attackers use what is already there. Python on Linux servers, PowerShell on Windows, JavaScript in browsers or Electron apps. This approach removes compatibility issues entirely. If the interpreter exists, the malware runs. And that is the dangerous part. The real weakness here is not execution, it is visibility. Organizations often underestimate how many interpreters are installed by default or introduced later through developer tooling, CI pipelines, or debugging environments. The third pattern is what you can think of as a dropper plus platform-specific modules. This is more structured and more scalable. First, a dropper lands and identifies the operating system. Then, it downloads the appropriate payload module. Finally, it executes native code tailored to that specific platform. This is common in modern botnets and espionage toolkits. And the reason it matters is simple, but often missed. Defenders frequently detect the dropper, but miss the second stage because it is only fetched at runtime and may never exist on disk long enough for traditional analysis. Now, the obvious question is, why is cross-platform malware accelerating right now? The first reason is cloud-first infrastructure. Linux dominates servers, but endpoints are still mixed. Attackers are no longer aiming for one system. They are aiming for the pipeline that connects them. The second reason is that developer environments are inherently heterogeneous. In a single organization, you will often find Mac OS laptops for engineers, Windows machines for business users, and Linux containers in production. That creates multiple entry points, but also shared credentials and shared tooling across all of them. And the third reason is even more important. Credential reuse has replaced system targeting. Modern malware often does not care what operating system it lands on. If it can steal tokens, SSH keys, or API credentials, it can pivot elsewhere. So in this model, operating systems stop being the target entirely. Identity becomes the target instead. At this point, there is a security misconception that still persists in many environments, and it is worth challenging directly. The idea is, we are safe because we use mixed OS environments. On paper, that sounds like diversity equals resilience. In practice, it often does the opposite. It expands the attack surface, increases patch inconsistency, fragments security tooling, and creates blind spots between OS-specific monitoring systems. And the important clarification here is this: the problem is not diversity itself. The problem is lack of unified visibility across environments. Now, when you look at detection, this is where multi-platform malware really exposes a structural weakness in many security stacks: OS-centric thinking. Signature-based detection breaks down first. Cross-platform malware often reuses logic but changes binaries, which makes signatures unreliable across builds. Endpoint tools are also siloed. Windows EDR sees Windows activity, Mac OS tools see Mac OS activity, and Linux logs are often separate. Correlating them becomes manual work rather than automated detection. And perhaps the most dangerous part is this: behavior looks normal in isolation. A PowerShell script on Windows, a Bash script on Linux, and a Mac OS launch agent might all look legitimate individually. But when combined, they form a coordinated campaign. The real failure is lack of cross-platform behavioral correlation. So what actually works in practice? The answer is not a clever detection trick. It is architectural discipline. First, you normalize telemetry across OS boundaries. That means security data should be unified authentication logs, process execution logs, network flow data, and privilege escalation events. Because if each OS is analyzed separately, attackers exploit that fragmentation by design. Second, you treat identity as the control plane. Since modern malware often moves laterally using credentials instead of exploits, you enforce least privilege, rotate credentials aggressively, and monitor anomalous authentication patterns across systems. Third, you start watching behavior chains instead of isolated events. Instead of asking whether a process is malicious, you ask whether a login on macOS preceded unusual Linux SSH activity, whether a Windows script triggered outbound connections to unfamiliar domains, and whether similar execution patterns are appearing across different operating systems. Cross-platform malware tends to reveal itself through sequences, not single points. Fourth, you reduce interpreter sprawl. Every unnecessary runtime Python, PowerShell, scripting engines expands the attack surface. This does not mean removing them completely, but it does mean restricting execution contexts and monitoring script engines more aggressively than compiled binaries. And when you zoom out, the conclusion becomes uncomfortable, but very clear. Multi-platform malware is not impressive because it is technically advanced. It is effective because modern computing environments are fragmented, loosely governed, and heavily dependent on shared identities. The real shift is not in malware sophistication. It is in the collapse of operating system boundaries as meaningful security barriers. If defenders continue treating Windows, Mac OS, and Linux as separate security worlds, they will keep missing the point. Attackers already stopped making that distinction. The battlefield is no longer the operating system. It is the connective tissue between them. Now, I want you to answer this like you are thinking through an actual investigation. If you had to design a detection system for multi-platform malware, which approach would you prioritize and why would you go with OS-specific detection tools for Windows, Mac OS, and Linux separately, or a unified system focusing on identity and behavior across all platforms, or network-level monitoring only while ignoring endpoint logs? Drop your answer in the comments and justify your reasoning. And here is the final challenge for you. Can you think of one real-world scenario where a Linux-only alert and a Windows-only alert look harmless on their own, but when you connect them together, it clearly indicates a compromise. If this breakdown helped you understand how multi-platform malware actually operates inside real environments, then like, share, and subscribe to BlueHat Cybersec Academy. This is part of the Malware Encyclopedia series, and in the next episode, we will go even deeper into how attackers chain cross-platform execution into full enterprise compromise paths.